So like I promised, I would put a parallel circuit example up. This is the same file I used for the previous video, and it's because it's the same activity we're working on. It's just the parallel circuits. How do you handle the parallel circuits? All right, so here's an example of a parallel circuit with 1, 2, 3 different possible paths. So remember the difference between parallel and series is series there's only one path. That's it. That's all you got to work with. Parallel you have multiple paths. 1, 2, 3 in this case. Okay? And so here's the big old ridiculous formula right here that you need to find RT. Okay? Just like with the series example, I put these over here in the order that you need to figure them out. Okay? And so the first move is figure out the total resistance. So these 3 resistors in parallel actually have a resistance that is, equivalent to as if there was just one path, if it was just one resistor in one path. How do you figure that out? Well, it's this right here. Okay, a bunch of reciprocals. So let me scroll down. Maybe this got to work. Let's figure out what we need to figure out. So RT, we figure out using this formula. So 1, okay, I don't know why that happened. 1 over 100 plus 1 over 1200. So just like any of the other examples, if you have it using kilo ohms or milliamps or mega ohms or microamps or whatever, you can't use that number. You have to switch. You're not going to use 1.2. You have to switch this to just regular ohms. All the Ohm's law stuff, these formulas for total resistance, remember there's 2 really formulas for total resistance. This one's easy. You just add those suckers up. First one plus second one plus third one. That's how it works for series, if you remember. It's parallel that's a pain in the butt. It's the big complicated formula. But no matter what, you always have to use regular ohms or regular volts or regular amps. You can't use 1.2. That's just wrong. Okay? And then you get 1. Why is that happening? Over 470. And so now it's purely calculator time. Okay? So if you have a graphing calculator, and you can just type, or a scientific calculator, we can literally just type it in as you see it. Just type it in as it goes. The only thing is put parentheses around the denominator. So you do 1 divided by, and then parentheses, 1 divided by 1 divided by 1 divided by so on. Okay? If you do that, if you got one like that where you can type it in, and as you see it, then you're good to go. If you're going to use the computer calculator, it's a little different. I can show you how you're going to really use there's usually a reciprocal button, a 1 over x button, or maybe a x to the negative 1 button. Okay, those will be your friend. Oh, that was a little smiley face. That's your friend. Okay, negative 1 that's a negative symbol. Just believe me. These 2 things will be your friend. One of these 2 things on whatever calculator you're using will be your friend when you do that. And if you have a calculator that isn't like a scientific calculator where you just see it as you're typing it in, we can talk about it in class. I can help you get it. Okay, so you do this, and what you do, it's 1 over, I'm going to show like the intermediate step. You get some tiny little resistance when you do that. Well, it's not even a resistance, it's the reciprocal of ohms. If you wanted to, you get 0.00, that's a lie, 0.01961 is what I have. Okay, and then you use, if you get this, you can actually then hit the reciprocal button here, and then you get 77.2 ohms. Okay, so that's the hard part. The rest is basic Ohm's law stuff. Okay, so if you do the Ohm's law stuff from the beginning of the activity, or from right here, if you understood this stuff, then you're basically home free. You just have to find current 4 times. Okay, and how do you find current? Well, by the way, time out before we move on. I wrote 0.2 because it was to the end, keep this number in the calculator. Its reality is, okay, well, or a much more precise answer is, let me put a little asterisk. It's 77 point this guy. I would really just keep this sucker in your calculator. Okay, that's all my calculator shows, but show all that. Keep all that. Okay? That's what you'll use in these calculations. Okay? And so how do you find it? How do you find the current? Like I said, it's just basic Ohm's law. So when you're finding current, it's V over R. What's R? I mean, what's R? Well, that's what we just figured out. What's V? 15 volts in this example. So we do, let's change colors just for the heck of it. 15 I equals V over R. Right, that's one of the Ohm's laws, or yeah, Ohm's laws forms. It's the helpful one for this one. So it's 15 over the 77.2. Okay, and you get 0.194 amps. And how you see it on the final exam, most likely, you won't see it like this. You'll see it as 194. I don't know why what does that sometimes. It's infuriating, actually. Milliamps. Nope, that's not what I want. Milliamps. Okay? And then you do the same thing for I1, I2, and I3, and it's like when I just said do the same thing. Well, I mean literally the same thing. You're using the same formula. You're using this, our friendly neighborhood Ohm's law, and it's going to be 15 over 15 over 15 over well, what? Well, make this a little smaller. Over the resistance within each branch. Now, actually, I've got these things, you know, I've kind of dropped the ball here. I didn't really tell you what I meant by I1, I2, I3. Here's the difference conceptually between parallel and series circuits. Parallel circuits are kind of vice versa. This is really misleading, this VR1, VR2, and VR3. That's all the same thing. Voltage is the same throughout a parallel circuit, okay? It's 15 volts here, 15 volts here, 15 volts here if you try to measure it with multimeter. It's current that changes. It's a different current here, here, and here. And that's I1, or IR1 maybe is what they say in the activity, but I assume you know what I mean. I1, I2, I3. So what's up is that you have all these electrons flying through, all right? And they have a charge, and really that's, you know, that's what current is. It's the rate at which the charge is changing. So it's kind of measuring how quickly the electrons are not, you know, they're traveling at roughly the speed of light, but how quickly the number of electrons that are changing from one point to another. Okay, and so kind of think of it as, you know, you're traveling along. You got all these guys going through, and then some of them go this way, some of them go this way, and some of them go this way. So the current is chopped up into 3 different parts. And how many go each different way? Well, it depends totally on the resistance. The more resistance, the less guys go that way. Okay? So it looks like the smallest guy's probably going to be R2. And then if you actually think about the math, that should totally make a bunch of sense. So you have 15 over R1, 15 over R2. This is why this is the smallest current. You're dividing by the biggest number, so mathematically it should make sense. And 15 over R3. Okay, and then, that's a 70. And so let me pause it and write all the, and go to the calculator and get the answers for you. And so that's what you get in amps, and then I just wanted to do the conversion while you guys were listening. But of course, you move over 3 spots here, boom, 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 and so it gives you 150 milliamps. This is 12.5 milliamps. And then this is a horrible equal sign, frankly. This is 32 milliamps. Okay, so if you add these up, 150 plus 12.5 plus 32, these add up to ballpark roughly 194. I was rounded off if you remember. So 150 plus 12 is 162, plus this is 194, boom. Okay? So this is where, you know, most of them, almost all of them go down the first path. Why? Because that's where the resistance is the lowest. Where the resistance is the highest, almost no one goes that way. And then that's in between. So there you go. That's parallel circuits and how you handle them. And hopefully this is enough to help you with the activity.